Thank you, everybody who came to the meeting today. I appreciate everyone who braved the storm and decided to join us. So today we are blessed with Guy in the Tuxedo's presence on Emulator Dev. And I have first a couple announcements before we start. Oh, we won third place in B-Sides Tampa. Nozomi has the prizes for the winner, so just a round of applause on everyone who participated. So thank you guys for for everyone who played. Sadly, this semester B-Sides Orlando has been officially canceled, and we'll potentially start up in the fall if I read the memo correctly. So we will not be going to B-Sides Orlando this semester, but keep an eye out in the fall for that. Our YouTube channel is active again. Check us out on YouTube at UFSit. We have uploaded 2 lectures already, the Docker lecture and the command and control lecture. We have not uploaded every single lecture we have recorded because, as you know, we are still trying to get used to like how like filming works and stuff, and we recorded some incorrectly without like audio and stuff like that. So we only have 2 lectures available, but they're pretty good, and this lecture will be up if everything goes smoothly too. And we are still having penetration testing practice tomorrow in CIC 312 at 6:30. So please come out to that if you can. And last but not least, please stay safe in with the virus and stuff. And potentially we will have next meeting also in person unless told otherwise by like CIC or you have the UF Dean in general. So without further ado, Guy in the Tuxedo will be presenting for us. Thank you.
What's up, guys? Who's ready to go through some emulator dev? Okay, let me...
Oh, post your questions in the chat if you have any questions in the Zoom link, or you can just come up here and say them in the speaker for Ryan.
Can I just like broadcast my screen now, or do I have to wait for something?
Yeah, no.
Start sharing and it'll replace what is being shared here.
Yeah.
We don't have to do anything on our end.
Okay, sure.
There we go.
Perfect. All you.
Okay, let's pull this up. Okay, cool. So emulator dev. You guys can see this?
Yes.
Okay, emulator dev. First off, what is an emulator? Does anyone have any ideas or anything like that? Actually, like the general people in there, can they like speak into the mic, or no, is that like not a thing?
Well, there's just a general mic for the whole room, so I guess we could try it, but I don't know if you would be able to pick it up. So
stand by.
Yeah, we could do a test. Yeah.
Okay, yeah, let's try it.
Somebody in the back say something. Ryan.
Yo, I heard that.
Can you hear me?
Yeah.
Okay. Yeah. Then it works. Yeah, we can ask questions.
So guys, can someone like tell me like what is an emulator or some idea? It doesn't have to be right.
An emulator is a piece of software that will replicate a normally physical system.
Yes, exactly. It's essentially software that like simulates an actual physical computer. And with that, the next thing, okay, that's what it is. What use can I get from an emulator? So why do people run emulators? Or what uses do people have for emulators? Any ideas?
You might not have access to the hardware.
Yeah, that's a good one.
They let you have more control over how a certain piece of hardware or software would behave versus running on actual hardware.
Yeah, it's a bit, you can do some things with hardware that you couldn't actually, that would be harder to do with actual physical hardware. That's a good one.
More controlled I/O.
I/O? In some scenarios, yeah. Also, another good reason is like, it will be easier to like, let's say you get one giant like bare metal server. From there, you can just spin up a bunch of like smaller computers off of there and just use them as there are just like 100 smaller computers. Like you guys know AWS runs like what 30% of the internet? Like all of that is just emulated computers. So yeah. Let me double check something, make sure I hit all the points I wanted to for this.
So you said AWS uses emulation for.
They use virtualization, so it's like VMware, but it's a different virtualization platform. I think it's Zen, if I recall correctly.
Yep.
But yeah. So with that, that's what an emulator is, what it serves. And let's say we want to actually like make an emulator. Anyone have any ideas of like how we would approach doing that, or like what things we need to consider while making an emulator? Well, okay. Actually, is someone going to say something?
Maybe an OS.
An OS, yeah. That's a good one.
Yeah. Speak up, Owen.
Would you need knowledge of the instruction set?
Yes, that is very important. Yeah, you need to know what the instruction set is, because if you don't know what the instruction set is, then you can't actually execute any instructions. Basically, some of the most important things is you need to know what the architecture is. So, okay, what the instruction set is, what the actual hardware of the architecture is, of stuff like registers, what registers are there, what do they pertain to, how many bits per register, all of that fun stuff. And most of that stuff is included with the architecture, so mainly the architecture. And after I go, how do you make an emulator? So with this slide, basically how you would go about at least making like a basic emulator is, actually let me pull up the slides. Okay. You would essentially like first understand, okay, how does this architecture work? And let's say I'm writing in C, how would I go about just implement that type of behavior? I'm going to be going into a lot of examples later on, like, okay, here's an instruction, this is what it does. This is an example of it running in an emulator, and this is how I implemented it. But yeah, and just in layman's terms, that's how you would do it. Also, one thing we're going to be covering, do you guys know what a register is? Can someone like just shout out like, oh, hey, this is what a register is?
D flip-flop.
Temporary hardware storage for data.
Yes, it's essentially like, temporary hardware storage used by a CPU. It's basically like, oh, hey, I need to store this data temporarily for some computational stuff. And you can store it there, and it's really fast. The architecture that I wrote an emulator for, and I'm going to be doing a lot of demos later on, is for a fairly simple architecture called Intel 8080. A version of it that was slightly extended was used in the original Game Boys, and it is a 16-bit architecture. One thing that with that, when someone says, oh, hey, this architecture is 64 bits, oh, hey, this architecture is 32 bits, what does that really mean for the architecture? What are some of the like implications of that? And does anyone know?
It's the word size of the processor, so which is usually the size of the register.
Yeah, it's like, let's say if it's like for Intel 8080, it's 16 bits. The max size you'll see of a register is 16 bits. Also, another big implication you'll see with that is, since a lot of the times what an architecture will do is it'll store a pointer in a register and then reference that value stored in the register as a pointer. One thing you'll see is the maximum address size corresponds directly to the bit size. So for 16 bits, it goes from 0 to the max 16-bit integer you can have. You guys are familiar with how, like, oh, hey, with like a 4-byte integer, you can only store so many values with it.
Yes.
Yeah, same thing. And like, you guys know why 32-bit architectures can only have 4 gigabytes of RAM, right? It's because if you, let's say, find the max, actually, let's fire up Python. This is the max value a 4-byte integer can hold, and if you were to take that as bytes and convert it to gigabytes, you would essentially get 4 gigabytes. So yeah. Basically the same thing. And now a bit about like the registers. There are essentially 6 different 16-bit registers. You have the B, C, D, E, and HL. Those are more for general use. I'll get into what that is in the next slide. You have specific use, which specific use was just a term that came up while making this, or it might actually be used, I'm not sure. Stack pointer and program counter, I'll get into that more. The final 16-bit register is split into 2 separate registers. The first, I believe, is an accumulator. I'll explain what that is later. The second is the flags, which is like an 8-bit register that is a bit different. I'll explain that in a second. First off, what is a general use case register? Anyone have an idea? Okay, essentially what it is like, you know how like when you're writing code, you'll have variables like, let's say, oh, hey, let's say we're solving a mathematical equation, we need to store some output in a variable. The code will use those registers for those values. And then brings us to like the specific use register, so the stuff like stack pointer and the program counter. Those are registers with predefined use cases, so you can't really like, let's say, oh, hey, I have a use for a register in this one particular scenario. You can't just overwrite it without causing a lot of fun behavior. The 2 main registers, you see this program counter and the stack pointer. Does anyone know what the program counter in a architecture does? Actually, I know you guys know this.
It points to the current place in memory that you're executing your code in.
Yeah. And if you're just to like overwrite that, that probably crash the code. So that's why you don't want to just use it generically. And the stack pointer, what does that do? Yes, it basically tells you like, okay, this is where the stack is. And yeah, so if you were to overwrite that, then you lose access to or you would lose where the stack is and you lose all the stack variables, and then that wouldn't be so fun. And that brings us to the last thing. What are flags? It's spelled with 2 G's for a reason. Anyone have an idea?
Flags with 2 G's.
Yeah, it's spelled like that for a meme on the next slide.
Oh, maybe when like you have a compare and the compare equals 0, then a 0 flag will go up. So
yes,
that's additional statement.
Yeah, essentially what a flag is it's a 1-bit value that indicates some behavior. And a lot of architectures you'll see that there's a 0-bit. So if you have some like arithmetic functionality, and the arithmetic output is equal to 0, that bit will be set. I'll be going into a bit more onto the 8 different bits and what they're actually going to do in a bit. On this slide is a cool guy called Randall Flagg, and then he may be involved with a Stephen King book about a super flu that wipes out humanity, so I thought it'd be appropriate to throw him in here, considering what's happening. Yeah, really cool guy. Next you have the... okay. Out of all the descriptions I've heard for a character, his description is by far the best. 1 sentence just tells me everything I need to know about that guy. But yeah, moving on. These are the flag values. There are 3 values that I'll cover right now. The other 5 I'll go into more detail later. The carry, the parity, the aux, the 0, and the sign, they all correspond to an event like the last instruction that was executed. The 1 flag right there, that's always going to be set equal to 1. And this 0, 0, and the 0, 1, those are always going to be set equal to 0. And these 3 flags, according to my understanding of the architecture, should not change. Also, I believe someone, I don't know who, but someone just mentioned that there's a 0 flag. Yeah, that's that flag right there. But any questions so far? Okay, I'm gonna take that as a no. So the rest of this talk, I just gave a brief high-level overview. now I'm actually going to like show you examples of like an emulator running with different instructions and how like I implemented the code for that. So let's minimize that. You all can see this VM, right?
Yes.
This ugly, okay.
Can you zoom in a little bit?
Sure. Is that good?
Perfect.
Okay. This emulator I'm using, it's one that's on my GitHub if you want to like follow along, meme around or whatever. I'll post it in the chat. Yeah, it's right here. Excuse the bad name. It's before it came up with like the rock song naming convention. Way better. But yeah. Let's go in here. So first off, actually, hang on, let me go into test cases. Okay. First off, we have these two instructions, MVI and move. Any idea what these two instructions do?
MVI is moves an immediate value into register. Move moves a value in one register to another register.
Yes, correct. Yeah, move just moves the, yeah, exactly what he said. I'm not, yeah. So let's show an example of that running. Come on. Test cases. Okay, here we see that instruction 0x0, it moves the value 0xde into d. So let's set a breakpoint for there, run it. Okay, here, yeah, we can see that the value, that d holds the value 0, but if we step 1, we're now at the next instruction, we see that it now holds the value 0xde. Also, did I cover what the 8-bit registers were? I think I forgot to. Essentially, you guys know how I mentioned beforehand there was B, C, D, E, H, L, those registers?
Yes. Yeah.
Okay, cool. Essentially, what the B register is it points to the greater 8 bits of BC. The C register points to the lower 8 bits of the C register. The D register points to the higher 8 bits of DE. That is why when you move the value 0xDE into the D register becomes 0xDE, and the DE register becomes 0xDE00. Does that make sense?
Yes. Yeah.
Cool. And then we're at this instruction. Right now we can see with the program counter being there, we're moving the value of D into C, so the C register should become the value of D. We step 1 and look at the registers, and we see, yeah, that move did happen. Now, any questions? I'm going to show the code in a second for how this works. Okay, no, I'm moving along. Okay, for move, yeah, for move, it's pretty simple. We can just like set run register equal to the next. Also, how 8080 defines this architecture, like I'll have an instruction for each move case, like for moving like a one register into another. And that's why you see like I'm laying different move instructions. And for MVI, there's a specific function I have here, which essentially what it does is you pass it the register the address of the register that you have in, and also the essentially the next byte over where the immediate value would be placed. And it essentially does the same thing. It also increments the PC. Now let me take a step back and explain like how I'm managing memory and everything. Emulate. Hang on a second. Flag set, emulate. Give me a second. Deactivate. Menu. Create CPU. Hang on, I forget what file I had that in. Emulator, Nightfall emulator, source, Riptech IR. Yeah. Debug commands. Okay. Okay, yeah, here it is. Sorry for the second. Essentially, first off, how I allocate the memory. With a 16-bit architecture, guys, what is the max size I can have with just addressing from 0 to 0xFFFF?
65 kilobytes.
Yeah, essentially that. What I just essentially do at startup is since that's a very relatively low amount of memory, I just allocate that entire block as one pointer, initialize it all with calc. That way, let's say I have a pointer to let's say 0x, I don't know, 40, I can just treat that as the index to the pointer and just have it that way. For the various, actually, let me show you the actual declaration of this in CP. Yeah. For the registers, what I do is for the 8-bit, each of the 8-bit registers, I declare them all as in UN8, which unsigned 8-bit integer. You'll see this one here, which is the arithmetic register. What that's going to be used for is that when you're doing a lot of arithmetic operations, such as add, subtract, the arithmetic operation register is what's going to be primarily used from the, and I'm primarily going to be like adding something to the arithmetic register and storing that value in the arithmetic register. For the flags, since they all are pretty much just like 1-bit values, I just have 8 different Boolean values for that. And for the stack pointer and the program counter, since unlike the BC, DE, HL registers, I'm going to be mainly interfacing with that as a, just as a 16-bit value. I just have those as 16-bit unsigned integers, and the rest of the stuff is essentially just debugger information. By the way, in case if you didn't, you probably caught it right now, but my emulator also serves as a debugger. Any questions so far? I will take that as a no. Okay. Moving on, we have, this is going to be a pretty simple example, but you guys know what NOP is? What the instruction NOP is? Anyone?
No operation.
Yes, what does it do?
Nothing.
Nothing, exactly. I'm gonna block 0. Yeah. Let's break at 0x10, run. Right now we're at this NOP instruction. We can check the value of the registers, and we step 1, and we see that none of the values other than the program counter changes since it's on the next instruction. But now we are at the INR instruction. It stands for increment. Anyone have an idea of what it does? Well, it essentially increments the register by 1. This time it's incrementing A. So we can take a look, what is the value of A? The value of A is 0, so after we step through this instruction to the next one. By the way, I forgot to ask, do you guys know what I mean by stepping through an instruction?
Yes.
What do I mean by it?
Executing a single instruction.
Yes, essentially just execute that single instruction and just break at the next one. So after I step through this one to the next one, I see that the A register has been incremented by 1. Yeah, let's take a look at the code for these. For NOP, hang on. Yeah, for NOP, I essentially, by the way, how I actually implement like executing all of the instructions is this isn't the most optimal way of doing it. I learned elsewhere, like there are a few different steps you can take to optimize it. But essentially, I just loop through all of the instructions and feed each instruction through like a switch statement. And I just check the opcode. In this instance, one of the NOP instructions is 0x0. For that, I can just break and do nothing else. Also, one other thing, are you guys familiar with how with certain architectures, all the instructions can be the same size, but with other different architectures, different instructions can be different sizes?
Yes.
Yeah. What this like for loop is doing is each time it runs, it will increment the program counter by 1. And if it's like NOP where it's just a single byte instruction, I won't have to do anything else with the program counter. But like, let's say it's actually, if it's an instruction that's like bigger than 2 bytes, like LXI, which I will pretty sure I'm going to show you guys later. I will have to like increment the program counter. So like, let's say if the instruction is 3 bytes, increment it 1 byte automatically with the for loop. So I'll have to increment another 2 bytes with the instruction itself. Any questions, or I'm just going to move on?
Yeah, no questions here.
Cool. Next up is the super complicated DCR instruction. Anyone have a guess of what that does?
Definitely.
Yes. Whoever said that, give that man like a pat on the back.
Oh, we will.
At least I'm assuming he's a man. It sounded like a man. It's 2020. Never know.
Yes, it's the wrong time of year for pats on the back.
Oh yeah, I forgot. Don't. Maybe if he's like, I don't know, like a serial killer or something, then it might be a good idea. But actually, I'm gonna stop memeing right there. This is being recorded. I don't want this to come up like 30 years later, just like you assumed that a person was a person.
All right, let's move on.
Okay. I'm getting derailed. Okay. Right now we are at program counter is at 11, which you can see is this instruction right here. DCRB, which is decrement by 1B. The value of B is 0x46. Can someone tell me if I made this emulator right, which there's a good chance I didn't, what would the value of B, the register B, be after I execute this instruction?
0x47.
No, it should be 0x45. Reason for it being is this is decrement, not increment. So we're decrementing it by 1, not incrementing it by 1. So yeah, when we step through it, yeah, we can see it's 0x45, and the reason for that being, yeah, again, it was decrement B, not increment. This code.
Brian, we have a question.
Yo, what's up?
How can you tell if they're signed or unsigned with how you're treating the variables in the register?
Well, with signed and unsigned, there's a particular. Sorry, my bad. With that would be more or less implemented, I believe, by like the compiler. The signed or unsigned bit is going to be the 8th bit of it. So it could be that like, let me think about this for a second.
Isn't the sign stored in the flag bit?
I'm sorry, what?
Isn't the sign stored in the sign bit, like the flag of
Yeah, is a sign flag for it. Yeah. And actually, what that does is it will be set if the 8th bit of it, of the actual value output is set. I'll get to that a bit more, but like for telling if it's signed or unsigned, I don't know of any particular instruction in the 8080 architecture right now that will just like automatically tell you like, oh, hey, this is signed or unsigned. I'm pretty sure what that will have to be is when when the instructions are actually being implemented, you're going to have to keep that in mind when the compilers are actually writing the code. Did that answer your question, Noop?
Yes.
Cool. Yeah. Be frank, was not 100% prepared for that question, but oh well, who's prepared for life? Yeah. For DCR, yeah, we just call the DCR function, which, let me pull up that file. It's right here, DCR. For this, we essentially just take the address of the register and subtract 1 from it. Also from that, you'll see these functions right here. I'll go into a bit more of what they do in a second. Essentially, right now, since we are making like an arithmetic operation, you have to check the output to see which of these 5 flags should be set. I'll get into that bit more in a second. Next up, we have the highly complex, super insane add instruction. Anyone want to get, it isn't totally, its full functionality isn't totally, what's the word? Relevant? Okay, you can't tell the full functionality of the add function just by looking at it, but you can pretty much assume what it does. Anyone have an idea what the add instruction does?
Adds B to A.
Yes, exactly. Yeah, pretty much. Yeah, that's the reason why you only see like one register like as an argument, like add B, add C, add E, whatever. That's because it is, yeah, yeah, it's always adding it from, well, to the A register. So let's set a breakpoint for the 10, at OX10. Let's take a look at the register values. And what is this instruction OX10? So we're adding B to A. We see that A is OX4 and B is OX4. Anyone want to tell me what the value of A will be after this instruction is executed?
8.
Yes, exactly. Unless if I did something horribly, horribly wrong, which, judging by how this talk is going, it's not out of the question. So let's step. And we see that it is 8. Yeah, another simple, really simple thing. And we can see for the instructions, this is kind of how 8080 defines its architecture or an instruction set. There will be a lot of different instances for the add where the like whether you're adding B to a register or C to the register, or A register, they will all get its own individual opcode. Anyone want to tell me what a particular advantage to that could be? For like, let's say having like 8 different add instructions where each one specifies, oh, hey, I'm adding this register to A. Oh, hey, I'm adding this next register to A. Well, okay. Did someone say something?
No, I don't think we know.
Okay. One particular advantage doing that, like, this might not be the reason why they made it. This is just something I just literally thought of. Well thought of before, is that if you hard code what the argument's going to be in the opcode, then when you're doing it, you don't need to like specify an argument to the opcode. So you'll see in a lot of different architectures, you'll have like an add instruction that it's only like one opcode for the add instruction, but you have to specify the arguments. And so that grows the instruction size. However, yeah, essentially it keeps the actual size of the instruction down, but it's at the expense of you have more opcodes that you have to deal with. So yeah. And when you actually look at the, why do I have so many of these? Math, why not math, where I'm doing add. Did I already show you the add instruction? Yeah, okay. So yeah, with the add, we just essentially dereference the pointer, take x, which is the value being passed in, we add it to a, we store it as a 16-bit int, yet the value that gets stored into a is an 8-bit unsigned integer. Can someone tell me why that is? The value we're adding up is a 16-bit unsigned integer, but the value we're storing in a is getting cast as an 8-bit unsigned integer.
Because A is only 8 bytes.
Yes,
Or 8 bits,
exactly.
sorry, 8 bits.
No, yeah, exactly. One thing you'll see a lot, I'm gonna pull up Python real quick to show you guys. Excuse my typo. Let's say you're adding values like F3 and OXDE. Each of these are a 1 byte, so they're both 8-bit values. But when we add them together, we get a value that's above 8 bits. Since also, you guys know that OX55 is 1 byte. Like 2 hex characters correspond to 1 byte. Just in case you guys didn't know, that's why I was doing that. You see that OX1D1 is the value of the output of that. And the reason why we need the unsigned 16-bit integer in the first place is because some of the flag operations, like the carry flag, they directly look to see, oh hey, was there a carryout? Is this new bit outside of the 8-bit set? It was. Okay, I'm gonna do some stuff. And let's say that from the final output, if let's say our value that we're adding to f is OXF3, and the value of the accumulator. Am I saying it right? Accumulator? Is that proper English? I don't know. And the value we're at, yeah, if OXF3 is stored in the accumulator and OXDE is the value we're adding to the accumulator, and this is the sum, what will be left in the accumulator? Actually, might be able to show you. See, let me. What are we at? We're at C 12. We're adding D next. D, then E. So let's step 2. Will this give us an overflow OX8 plus? Yeah. So right now we are at this instruction, so we're adding E to the accumulator. The value we're adding to A is, the value stored in A is OXA0. The value we're adding to A is OXBA. So essentially we're doing this. Anyone wanting to tell me what the value of A will be after I run this instruction? With this, that's going to give me this overflow.
0x5a?
Yes, exactly. The reason for that being is like when there is an overflow, essentially the value that remains in the register with the add instruction is the lower 8 bits of the output. And when we look at, oh hey, what's the lower 8 bits of the of this value, we get OX5A. So if we step through it, we see that, oh hey, that's the value in it. Okay, any questions? Okay, cool. Next up is the sub instruction. Pretty similar to add, it's just with subtracting instead of adding. Break at 0x10. Run it. We see that the value of A is OX55. Value being subtracted from it is AB. So OXFF minus OXAB is OX54. And when we step through it, we see that that's the value left over. When we look in the code to see how it's done, sub, yeah. The sub function, realistically, that I implemented, since it's always going to be subtracting from A, the only argument you really need other than like the CPU being used is the B register, or the register being subtracted from. And when we go over to math.c, I need to get rid of some of these tabs. One thing you'll see with this is I'm not subtracting it directly. I believe this is called like subtracting with like 2's complement or something like that. Essentially, what I do with this is I do a binary not. Do you guys know what that is? Essentially, it's when you like, let's say you have a number that's like like OX54, for instance. It's when you take the zeros and the ones that comprise the actual number and you flip them. So when we not it, binary not. Okay, I did something wrong with that. Okay, but yeah, so let's say if you had the number that was that, the knotted version of that would be that. And just with how this works, to subtract a number, you can do a binary not, add 1 to it, and then just take that number and add it to whatever value you're trying to subtract it from, and you get the same behavior. And yeah, any questions with that? Okay. Give me just one thing I want to show you guys. Architecture. Let me pull it up. No. Okay, yeah, here it is. This is a total list of the instruction set for 8080. Just can you guys see it? Just fine. Read it. Yeah.
Really?
Oh, okay.
Can you see? Oh.
Okay, if you guys can't see it, oh well. Yeah.
Oh wait, we can see it. Yeah, we.
Oh,
yeah.
okay. One thing you guys might see, like you see that, oh hey, there's like a value for move to move pretty much any register into any other register. Yeah, there's a lot of add instructions to add each individual register to the accumulator. And yeah, one thing you might see is you might see this register M. All that is it essentially treats the HL 16-bit register, takes the value stored in it, treats that as a pointer to some memory address, and then just treats whatever that value is as like a register. So like let's say move HM, what that would do is that would dereference the HL register, take that value, move it into H. Yeah. I'll show a bit more I'll show a lot of examples of like dereferencing addresses in a bit. Memory manage block. Oh wait, hang on a second. Actually, I think I have a demo prepped for this. One particular thing, block, no. Block 1, test cases 0, 5. Okay, yeah, let's set a breakpoint right there. So right now we are at this instruction, move H into M, which will essentially it dereferences the HL register and will move H into it. Looking at this right now, we see that HL points to the address 4040. So when you take a look at 4040, right now we see that it's equal to 0. And we also see that H right now is equal to 40. After this instruction is executed, what will this address be and why? Well, what will the value stored to that address be and why? Well, it's going to be 40 since it's just dereferencing the pointer stored in M and moving H into it. So just go by 1 and we can see, oh hey, it's equal to 40. Yeah, that's an instance of it dereferencing a value and dealing with pointers. Okay, next up, pretty simple example. Test case 010. Okay, now we're going to be dealing with the instructions INX and DCX. Anyone want to give a guess on what they do? Shoot out unicorns, summon dragons, cause the end of the days. All acceptable answers.
Is X a register?
Oh, I'm sorry, what?
Is X a register?
X is not a register. B is a register, but X is not a register. Well, essentially, you guys remember the INR command, how it just increments a register by 1? Basically the same thing. The only difference is instead of incrementing an 8-bit register, it increments the 16-bit register. But you might be looking like, hey Ryan, this is just a B. Like that's an 8-bit register. Like you're lying to us. One thing I've seen a lot with this architecture and kind of like copied it over into like my own disassembly, which you're seeing right here, is when you have an instruction that like takes a 16-bit register, they'll just call it like the first letter of it. So they'll refer to the BC register as just B, the DE register as just D. And I kind of like follow that standard. I don't recall seeing it explicitly stated anywhere that you're supposed to do that. I just did it because I don't know. I just wanted to. So this is just going to increment the B register, well, the BC register. So this should turn to 3673, and the C register should get incremented by 1. And when we step through it, we see that's exactly what happens. The C register gets incremented by 1. And let's step through to a decrement. Decrement essentially does the same thing, but instead of incrementing a 16-bit register by 1, it decrements a 16-bit register by 1. This is going to increment OXB800 by 1. Actually, no, not. Sorry, it's going to decrement BC, not DE. And when you step through it, we see that it is OX3672. Anyone want to tell me what like this would be after being decremented? Since right now we're at wait, no, we're not there. We're here, yeah, on this instruction, decrementing DE by 1, with DE being the value OXB800. Well, should be OXB800 minus 1. OXB7FF in a new step 1. You see that that is indeed the value. Let's take a quick look at the code and how we implemented it. In emulate INX, okay. INXB. We see, like, for the since with my implementation of the emulator, I always treat like the BC. I don't actually have a value stored for the entire 16 bits of BC. I just have 8 bits stored for B and 8 bits stored for C, and whenever I need to reference BC, I just take those two values and do what I need with them. I have an INX defined for just dealing with 8-bit registers, and let me see what I have. Okay, math.c. You can see here essentially what I do is I just check, okay, is the, well, for incrementing, I just check, is the lower 8 bits, is that going to overflow into the higher 8 bits? It's not, just add that to 1. If it is going to overflow it, then just set the lower 8 bits equal to 0, because when it overflows, that's what the value is going to be. And then just add 1 to the higher 8 bits. Yeah. Any questions there? And let's, yeah. If not, I'm going to move on to the next example. One of the instructions we're about to deal with next is called dad. So, yeah. Okay. First off, we have the LXI. You guys remember the move immediate? Kind of the same thing, but LXI is for a 16-bit value. So when it's LXI-B, after this instruction is executed, this value 9572 should end up in the BC register. So we can run it, see that it's equal to 0, and after we run it, we see, oh, hey, it's 9572. And next up, we have the data instruction, which essentially, actually, give me, okay, I'm gonna skip the data instruction for now for
Is that something you created?
the data instruction.
Yeah, or is it like a means thing, or is it part of the architecture?
No, it's actually part of the architecture. It's somewhere on this chart. Where is it? Dad. Top. Yeah, it's right here, dad. Yeah, reason why I'm skipping it is just in my notes it's unclear and I forget exactly what it does, and I don't want to like burn time like just quickly looking up what it does, or like stepping through it and just figuring out from there.
Yeah, that's fine.
Yeah. Next up we have the stacks instruction, which brings me a bit of joy in this very humorless, dry talk. Okay, right now, I'm gonna break this stacks instruction right here. Essentially, what this value would do is it takes a 16-bit register as its input. In this case, it's a BC. It treats that value as a pointer and will store whatever the value of the accumulator is at that address. I believe the instruction stands for something like store accumulator. In this instance, A is equal to OX10 and BC is equal to, we can see that it's OX2020. So after this instruction executes, the value at OX2020 should be 10, or OX10. Yeah. Also, you guys, do most of you have experience using a debugger? When I like type this X space 1 space address, is that just like magic voodoo stuff? Okay.
It takes 1 byte, right, for at that address.
Yeah. Essentially, with this command, since what I'm doing is I'm specifying, hey, I want to examine. Tell me what's at this address. Need 1 byte from here. Let's say if I wanted 10 bytes, I could just do OX2020, and I would get 10 bytes. Yeah. So you can see that.
Decimal?
I'm sorry, what?
You display them as decimal instead of hexadecimal?
I don't believe I implemented the feature because I never had a need for it. It wouldn't be like much. It wouldn't take, as you know, it wouldn't take very much to display it as decimal. But like, I just never felt the need to implement that functionality into this.
I'm curious to know how the emulator works in a bigger picture. Like, how are you running these instructions on the emulator? Is it reading from a file? Like, how does that work in terms of
Oh,
I/O?
excellent. Essentially, what I do, how this emulator is working. You see how I am run the emulator itself is called Nightfall, and let's say I'm picking just which one block. You see how with it I'm specifying a file.
Yeah.
This file right here actually holds valid like Intel 8080 instructions. So with that, let me
Cat the file. I don't believe it.
essentially, yeah, I just read in the file. Actually, first I create the CPU. I scan the binary, which that essentially just, oh hey, scan in all of the instructions. With that, hang on, let me scan. Let me. Where is that function exactly? Give me a second. Emulator. Where's that function name again? It was scan binary. Utils.c. Okay. Utils.c. Yeah. I open up the file, read it, and yeah, I just scan it into memory. And then from there, I specify, like how I did it with my emulator, is I scanned in all the instructions starting at 0x0. When I was reading through the architecture manual, I might have missed it. I remember spending a lot of time and not finding it. I don't recall seeing anywhere that specified where like, oh, hey, this address is where the instructions should start or the stack. So I just kind of picked my own values from there. Yeah. Although reasonably speaking, as long as like off the top of my head, as long as your compiler is aware of like where values are starting in memory, it shouldn't matter exactly where you're starting your memory regions as long as they're within the valid range. But you might want to fact check me on that. Okay, that's a bit derailing. Anyone else have any questions, or should I just get back?
Show the content of the file.
Show the content. I'm sorry. Oh, sure. For that, CD tools, Binja. You'll be using Binary Ninja for this. Open. So essentially, have you guys ever like looked at a binary file before? I'm assuming most of you guys have.
It's not visible.
Yeah, we can't see it.
Oh yeah, no, I'm still pulling it up. I just asked that question while I was pulling it up. Block 0. Yeah, here. Essentially, literally, like what it is it's like I just like when I was making these. I can't recall if I wrote a like just like simple compiler for this, or if I just hand wrote the instructions myself. But I literally like typed out these instructions. So like here we have test case OE, which that one starts with an instruction at 6, which if we look at our instruction set, 0, 6 MVI, so it's moving an 8-bit value into B. It should be, by this look of it, 45. So if I understand this correctly, if we look at the disassembly for this, the first instruction should be move immediate into B, OX45. And let's fact check me on this. And yeah, we see that the first instruction is move into B, OX45. You see with the next instruction, it starts here. Since this is a 2-byte instruction, it's OXE, which we see here is move immediate into C, an 8-bit value. We see that the argument here is 85, so it's move 85 into C, which we see that that is the instruction.
You have a question on the floor?
Yeah.
Yeah, I have a question. You know how like with ELF files and stuff, there's like a little bit of like overhead as far as like how the sections are laid out and how the memory can happen and things. For actual Game Boy files, does it actually start with straight code that is running, or is there some sort of like an OS that makes an entry point?
With actual Game Boy files, I'm pretty sure it doesn't just start with like straight instructions. I'd be very surprised if it does. With that being said, when I was doing this project a few years back, I was mainly focused on just writing an emulator. I didn't actually take this as far as like extending it to an actual Game Boy functionality. So I don't have as much experience with actual like dealing with like old Game Boy ROMs as I would like to. But to answer your question, I'm pretty sure no. However, I don't recall ever like confirming that. Does that answer your question, Noop?
Yeah, that answers my question. Thank you.
So I have a question, another question. So this so you would feed this Game Boy files and then execute the code, but it doesn't actually, because you don't have any like a ROM or anything to show user interface. It doesn't actually perform any Game Boy functionalities, just the literal instructions that would be happening underneath the hood of a Game Boy, right?
Yeah, pretty much right now with this project, this emulator I just made, I just wanted something that could like write code. So I just essentially designed it so it could just like run the instructions and also have a debugger attached to it, so I could just like look under the hood and see what it was actually doing. You couldn't throw this thing a ROM file. Sorry, my bad. You couldn't throw this thing a ROM file and just play Pokemon, sadly. Although I may do that in the future, but for like right now, it doesn't have that functionality. Sorry for being a disappointment.
That's okay. It's cool.
Okay, cool. Next up, any other questions? Okay, next up we have the LDAX command, which how are we doing? Oh, it's 6:40. I need to hurry up. How late do your guys' test case? Oh, not test cases. Meetings go.
7.
Okay, I'll be able to finish up by then. 0x015. Although LDAX, essentially it's with STAX, we were storing the accumulator into a memory address. Here we're loading the accumulator with a value stored at that address. So let's just break at OX16. Run there. We see that this is LDAX B, so it's loading from the pointer stored in BC. We see that value is 2020. When we look to see what's there, we see it's 22. After we execute this instruction, because of that, the register A should be 22. So when we step, we can see that it's indeed 22. Yeah, code is pretty similar. Actually, here, let me pull it up so don't shortchange you guys. Emulate, LDAX. Yeah, emulator just calls this function, which if we look at it, LDAX, yeah, it's just literally loading this. It's loading A with a pointer, the pointer being this uint convert. That's just a function I made just so I could pass it to 8-bit registers such as like B or C, and it would give me the 16-bit value. And I just treat that as an index to the CPU memory pointer, and then just store that value in A. And next up, we are going to be taking a slight detour. You guys remember flags? There are really 5 of them that actually change. There's 0, sign, carry, parity, and aux. I'm going to quickly go through like which each of the flags do, and we're about to hit some arithmetic instructions, which I'll be able to demonstrate the actual behavior of them a bit more. 0, as we've said before, what that covers is if the arithmetic operation is equal to 0, it's set. If not, then it is not set. By the way, what I mean by set is setting. When I say I set this flag, it just means I set it equal to 1, so the value is 1. If I like unset it or like not set it, or I forget what the exact term for it is, it's going to be set equal to 0. So yeah, set. Actually, I'm not going to type that out. Sign. So within most of the time with the values are going to be 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. If the 8th or the greatest bit is equal to 1, the sign flag is set. If it's equal to 0, it is not set. The carry bit is set if there's an overflow. So let's say if we added 2 values together and we get a 9-bit value where the 9th bit is set, then the carry bit is set. Do you guys know why I care if there is an integer overflow? Like, can someone just shout out like, hey, this is why keeping track if there's an integer overflow is important?
Security reasons?
Yeah, not even just that, like other than security reasons, but like, let's say you're adding 2 8-bit values together that give you a 9-bit value. If you keep track if there's an overflow, that allows you to actually deal with that and get the arithmetic outright. I haven't covered it too much yet. However, there are some instructions that actually will implement the carry with it. After that, we have the parity bit, which the parity bit's a bit interesting. Let's say you add 1 plus 3 and it gives you 4, which in binary will be 1, 2, pretty much be this value right here. If the number of 1s in the output value is even, the parity bit is set. So in this case, number 4, it only has 1 1 in the output value. So it is the parity bit in this instance with 1 plus 3 equals 4 will not be set. Also, the inverse is true. If the amount of 1s is equal, then you could also check for the amount of 0s. Since it's an even number numbers are being pulled from, it works out that way. And then the final flag, oh, by the way, I haven't actually found out what the use case for the parity flag is. I just implemented it. Last off, we have the aux flag, which that's similar to the carry bit, except this is set if there's a carry out of the bit at index 3, so essentially like the 4th bit, the 4th greatest bit. If there's a carry out of that, then the aux flag is set. Now, okay, let's show you some examples with that. Block 2. I'm gonna be just briefly going over like add instructions again, so I can just show you guys. OX10, run it. Right now we are adding B to A. B is 4, A is 4, so the output will be A, 8. My bad. Yeah, the output will be 8. With this, obviously we're not gonna have a carryout. Well, we're not gonna have an integer overflow, so that's not gonna happen. That bit will not be set. But let's carry on. With these values, the bit at index 3 is not set since it's only the bit at index 2. So we're not going to have a carryout of that. So the the aux flag won't be set. The sign bit, which is the 8th greatest bit, won't be set. So basically, none of the flags should be set since none of the conditions actually happen. So when we step, although except for the 1 flag, since that never actually changes. Step, and yeah, we see that condition holds true. Yeah. Next up, let's cover. You guys know what binary ANDing, ORing, and XORing is?
Yeah.
Okay, what is it? Just one of them.
And it's like a bit mask, and you can use it to like say if this bit and the corresponding bit in the other integer are both set, then keep it as a 1. Otherwise, turn that bit into a 0, for example.
Okay, yeah. This right here, ORA, it's ORing the B register against A and storing it in the A register. The A register is 0. The B register is OXAB. So we're ORing 0 by AB and storing that value in A. Does someone want to look in their magical glass ball and tell me what the value of A is going to be after this instruction is executed? Did I hear something?
What are you ORing with?
I'm sorry, what?
What's the operation?
Oh, operation. ORA, we're ORing A by B and storing the value in A. That's what the instruction is. And the value of A is 0. The value of B is OXAB, and we are right here.
OXAB?
Yeah.
It's OXAB.
Yes, exactly, because like we can just look right here. AB ORed by 0. 0 ORed by anything is whatever that anything is. So we can step and see, yeah, it's AB. Next up, I just have like 3 more mini demos. Actually, let me show you the code for it. Pretty much just calls this function right here, ORA. Actually, OR. Yeah, we take that value, OR it by A, and then run it through the various sign functions, well, flag functions, which handle that. Also, I'm going to show you a bit about how those flag functions operate. For like, let's say the parity flag, we just essentially loop through the 8 bits of that, try to end it by 1, shift the value to the right by 1 each time. Every time that we detect that, oh hey, there is a bit there, by ending it with 1, we just increment the counter, and at the end we just mod it by 2, which is just checking if it's even. If it's even, we set it. For the carry flag, it's really easy. We can just end it by OX100, which that is essentially just 1 followed by 8 zeros. And if that value is not equal to 0, we know that 9th bit has to be set, so the carry flag is set. That just gives you a bit of introspection to how that works. Yeah. So with this array, let's cover XORing. So right now, we are, I believe with this instruction XOR A, where we are XORing A by A. Can anyone tell me what the value of A is going to be after this? We are XORing the A register by itself.
0.
Yes. I got this right. Yeah, because anything XORed by itself is 0. Yeah. Next up, we're going to be covering push and pop. Just from like knowledge of like other architectures, can someone tell me like what those operations really do? Maybe like a high level overlook.
Push puts value on the stack, and pop takes it off the stack. Usually it's right.
Yeah, exactly. Push will like take a value usually from like a register and move it onto the stack. Pop will take a value from the stack and move it into a register. Let's go to OXE. And we see right now we're on this instruction right here. We see, oh wait, hang on, wrong command. This will push BC onto the stack, which we see BC is OXDEAD. And the stack pointer is OX4000. Again, the reason why I picked that as a start is just because that's the value I just came up with. I didn't find it in an architecture manual anywhere. Also with this, what it'll do is it will decrement the stack pointer by 2. So that way it increases the size of the stack for me to store those values. So when we step 1, we see that, oh, hey, that value got decremented by 2. And we look at those values. We see, oh, hey, it's the value stored in BC. And incidentally, when we go to right now, where are we? We are at OXF. So that instruction, let's go to the first pop. So 12. We see right now the stack pointer is here. So we pushed all of these values onto the stack. This is going to pop the value on the top of the stack, so this OX2 and OX66, into the HL register, and then it's going to increment the stack pointer up by 2 to essentially like shorten the stack, since by popping values off the stack, you're essentially removing it. So when we step 1, you see that, okay, it got incremented by 2, and the HL register got the values that we expected it to get. Any questions? Nope. Just gonna quickly show you the code for these instructions. Stack push. Yeah, we just with a push, we just take the, at least with this, when dealing with like 16-bit registers comprised of 2 separate 8-bit registers, we just decrement the stack pointer by 1, store the value of the first register there, then decrement it again and do the same thing. And pop is basically the same thing but inverted, and instead of storing values, we're loading values. And lastly, for the last part,
I have a question.
yes.
There's no offsets, right? I don't see an offset. Like you can't. It's not like x86 or 64-bit architecture where, and like there's an offset from EVP and you can get values like that, or is it just like off the stack?
In terms of like getting an offset like OX RBP, like stack pointer -5, I haven't seen anything like that in any of the architecture manuals or any of like the instructions. It might exist somewhere, but I haven't actually seen it with this architecture yet. Yeah. Moving on to the last example, we're going to be dealing with like branches and jumps. So 33. Oh wait, no. Maple. File not found. Hang on a second. Block 3. Okay, I'm gonna go with that one. Okay. Wait. Okay, that explains it. I made a typo in my notes with it being in the wrong block. Test case 033. Okay. So with here, we load the value A into 66 into A, load the value 0x70 into B, and then we do the CPI, which it stands for compare immediate. Essentially, what that's going to do is it's going to compare it the immediate value against the accumulator. And how it does this is essentially just subtracts the value from the accumulator and then just sets the flags accordingly. It doesn't actually change the value of the accumulator. So we can set a breakpoint for there. 0x4, we see that the value of A is 66. Since the value is being compared against is OX66, and all the compare essentially is it just being subtracted. It's subtracting the value from the accumulator and setting the flags accordingly. The 0 flag should be set after this, which if you look at this, the 0 flag is set. And we see that the current instruction we're at is jump if 0, so jump if the 0 flag is set to OX10. So the next instruction we should essentially jump from here to there, and we did. So now what's happening? Where are we? We're going to compare B against A, which, looking at the values, B and A are not equal, so the 0 flag is not going to be set after this. Which, if you look at it, yeah, the 0 flag is not set. And also we see that B is larger than A, so when we subtract it, we get a negative number. That's why the sign flag is set there. And where are we? Program count, we are at instruction 11. So right now we are here. Jump of not 0, the 0 flag is not set, so we should be heading there, making the jump, and we will end up here at that MVI call. And yeah, we are there. We're gonna move an immediate value of x93 into A and then call the sub function. And with call, are you guys familiar with the difference between a jump and a call? Can someone tell me what the difference is between a jump and a call?
What's that?
Yeah, a call essentially will save a return address. That way, when the subroutine is done executing, it can return back. The return address will be the instruction after it. So this call, it should return to this jump. Yeah. And then, yeah. So let's look at the stack pointer beforehand. OX400. We see that it got decremented by 2, which LX021, which is the instruction of where it was where it should end up at. Here we are at OX4F, where it's just going to add B to A, which with these values right here, we can see that. Yeah, that looks about right. And then afterwards, it's going to return. When it returns, the stack is going to shrink back, which it did. And then finally, it just jumps to OX4C, where it just nops and ends. And yeah, that's it. Any questions?
No questions on this side.
Cool.
Well, thank you so much, Ryan, for a great presentation. Round of applause, please, everybody.
Sorry for boring you guys half to death. Yeah, if you want to delve more into, if you want to look deeper into how this emulator works, I sent the link. It's on my GitHub. Feel free to ask me any questions like, oh hey, why did you write such a crappy emulator? Yeah.
That's fine.
Cool.
Yeah. Well, man, thank you so much. We appreciate to have you, and thank you for such a great presentation.
Cool.
All right.
Bye, Ryan.
Bye.
Bye.
See you later.
Oh, yeah. How do you stop recording?
Where's the life?